6.1 Integration by Substitution, Day 2. So we talked about integration by substitution in the last lesson, and in this lesson I want to see if you can answer which one of these 6, and there's more than one, requires that you do use substitution in order to find the integral. If you said everything on the right-hand side, you would be right. Everything on the right-hand side, they all require use substitution. Let's talk about that in a bit more detail. For this first one up here, we would let u equal to 3x squared minus 5 because that's like an inside function. For the second one, I would let u equal to the x squared plus 3 because you can see that the derivative of x squared plus 3, it's not quite x, but there's a constant there that you can take care of. And then for the last one, I would let u equal to the inside function, which is 2x. Now for the left-hand side, in order to integrate there, I would just distribute the x. For this middle function, I would split that up as x squared over x plus 3 over x, and then do the integral. I'd simplify and then do the integral. And then for this one, this is just a product of two functions, so you actually can just do the antiderivative of 2 sine of x, which would be pretty easy. What I want to talk about now is something that you don't have to do, but I like it. I call it the linear shortcut. Essentially, some textbooks, not your textbook, but some textbooks will talk separately about integration involving a linear expression mx plus b. These are the situations where we would be looking at. So e to the mx plus b, sine of mx plus b, 1 over mx plus b, and then mx plus b raised to some power. So if you recognize that you have one of these situations, then you can do this particular shortcut. And the shortcut is almost the same for all of them. You would do 1 divided by the slope times the antiderivative. And the antiderivative of e to the whatever, of course, is e to the whatever. So it'd be e to the mx plus b plus your constant of integration. For the sine, and of course you can also do this for a cosine, but for the sine of a linear function, we're going to do 1 over the slope, and then the antiderivative of sine is negative cosine, so let's actually put the negative out there, cosine of mx plus b plus c. For the next one, the antiderivative of 1 over mx plus b, we're going to do 1 over m, and then the antiderivative of 1 over something is going to be the natural log of that something. So that's times the natural log of the absolute value of mx plus b plus c. And then for the next one, we would do 1 over the slope, so 1 over m, and then the antiderivative of stuff to a power is going to be that stuff, so mx plus b to the n plus 1 power divided by n plus 1, that new power, plus c. And then we can put an additional condition on here, since we're talking in general terms, that n cannot be equal to negative 1. And if the reason for that is that if n is equal to negative 1, then you have this situation that's mentioned right here. So again, I call this the linear shortcut for integrals, and I'm going to show you 2 examples using this process. So in this example is actually a word problem involving velocity and displacement. We're given the velocity of a particle is given by that function, and then the displacement of the particle is defined as s. And then they also tell you that s of 2 is equal to t, so that basically means that 0, 2 is going to be on the function s of t. We're going to use that to solve for our constant of integration that we have done in the past. So first of all, remember that the position or the displacement is equal to the antiderivative or the integral of the velocity function of v of t dt. So in other words, that's going to be the antiderivative of e to the negative 2t plus 12t dt. And that's going to equal your displacement function. Here's where I have a situation where I'm going to use that linear shortcut, because this right here is e to the negative 2t. So the antiderivative of that is going to be 1 over the slope, which is negative 2, and then e, the antiderivative of e to the stuff, is going to be e to the stuff. And then the antiderivative of 12t is going to be 12t squared divided by 2, and then the plus c. So just cleaning it up a little bit, we now have negative 1/2 e to the negative 2t plus 6t squared plus c. So that's our position function. We're not done yet because they also gave us the fact that 0, 2 is on the function. So I'm going to use that information to actually solve for my constant of integration. So I'm going to say that 2 is equal to negative 1/2 e to the negative 2 times 0 plus 6 times 0 squared plus c. So 2 equals negative 1/2, and e to the 0, that's just going to be 1. And then, of course, 6 times 0 squared is going to be 0, plus c. So I really have 2 equals negative 1/2 plus c. So I just need to add a half to both sides. So that's going to be 2.5, or 5/2 is equal to c. So now I know that my full displacement function is negative 1/2 e to the negative 2t plus 6t squared plus 5/2. I want to point out that in this problem, if you didn't do the linear shortcut, you would have to separate these two integrals and do the antiderivative of the integral of e to the negative 2t dt plus the integral of 12t dt. You don't need to do u substitution for the 12t bit, but over here you would have to let u equal to the negative 2t, and then the du would be negative 2 dx, and so then du divided by negative 2 is equal to dx, and then you would have to proceed from there. So in order to avoid all of that extra work, that's why the linear shortcut is very useful. Let's look at another one where I'm going to use the linear shortcut. And this one is actually also different than what we've done in the past, because now we have a definite integral. I have the lower boundary and the upper boundary, so that means I'm going to have to plug those values in and get an actual number. So for the linear shortcut, that's going to be equal to 1 over the slope, which is 3, and then the antiderivative of sine is negative cosine. I'm going to put the negative out here. So negative, and then 2 cosine of 3x. And then we don't do the plus c with the definite integrals. Remember, we do the square bracket, and then we rewrite our boundaries there. So I'm just going to clean that up a little bit. That's negative 2/3 cosine of 3x from 0 to pi over 3. So now I will plug in my boundaries. Top boundary first, so negative 2/3. I'm going to simplify. So I need to figure out the cosine of pi and the cosine of 0. So remember that pi is over here, and the coordinates are negative 1, 0. 0 is here, the coordinates are 1, 0. So the cosine of pi is negative 1, and then the cosine of 0 is positive 1. So I have 2/3 plus 2/3, which is 4/3. And if I had wanted to do the u substitution, which we're going to do in another example here in just a minute, we would have to let u equal to the 3x. All right, let's talk more about u substitution with definite integrals. So I have 2 more examples, but in neither one of them we can use the linear shortcut. So we're going to have to learn actually that we also have to adjust our upper and our lower boundaries. So when I look at this problem, I can see that I have some stuff inside of a power of 2, and also that if I take the derivative of that stuff that's on the inside, I'm going to end up with like a 9x squared, which is not that different from the 18x squared. But as we do the menu correctly, then we can see how to work with that. So we're going to let u equal 3x cubed plus 3. Remember, we do a du dx, which would be 9x squared. And we ultimately want to solve for dx, so we can say du is 9x squared dx. Du over 9x squared is equal to dx. Okay, so that's all part of the menu, but I'm actually going to do something else with my menu. I need to find a new lower boundary, and I'll need to find a new upper boundary. So when we do these boundaries, or the boundaries that are given to us for -1 and 0, those are the boundaries in terms of x. But we are about to write our function all in terms of u. So that's why I need to have new boundaries that are for u. So to find your new boundary, you're just going to use what we set up for u. So we're going to have the u equals 3, and instead of x, I'm going to put -1 cubed plus 3, because -1 was my given lower boundary. So that's equal to 0. And then my new upper boundary, we're going to plug in the 0. So that's going to be 3 times 0 cubed plus 3. And so that's just equal to 3. So now when I make all my substitutions, I also have to substitute for my boundary. So now we're going to do the integral from 0 to 3. And then I have the 18x squared. I'm not going to substitute that. U squared, and then of course instead of dx, we're going to have du divided by 9x squared. So a couple of things. The 9 and the x squared, that's going to reduce to 2. And then the 2 is a constant, so I can take that outside the integral. So I have 2 times the integral from 0 to 3 of u squared du. Now I'm going to do the antiderivative of u squared, which is u cubed over 3, and we're going to we're going from 0 to 3, and we can put that 2 out in front, and you can include the 2 in your calculation, like put a square bracket there, or you can multiply by the 2 later. I'm going to go ahead and multiply by the 2 while I'm plugging in the numbers in. So that's going to be 2 times 3 cubed over 3 minus 2 times 0 cubed over 3. 2 times 3 cubed over 3, that's 18. And then that's 0 over there, so my answer is 18. All right, let's have a look at number 11. So I'm going to first let u equal the inside bit, that's 4x squared plus 4. So du will be 8x dx. So du divided by 8x is dx. For my new lower boundary, we're going to have u equals 4 times 0 squared plus 4, which is 4. And then for my new upper boundary, u equals 4 times 1 squared plus 4, which is 8. So now I'll make my substitution. So I'm actually going to do the integral from 4 to 8, and then that's 16 over u squared, and then instead of dx I have du over 8x. Whoops, there's supposed to be an x there. 16x over u squared, and then du over 8x. The x's, of course, go away, and again, the 16 and the 8, that reduces to 2. That's a constant. I can take that outside, so I have 2 times the integral from 4 to 8 of 1 over u squared du, which we can call that u to the negative 2 du. And then the antiderivative of u to the negative 2 would be u to the negative 1 over negative 1. The boundaries are from 4 to 8, and of course we have that 2 out in front. So we can call that negative 2 over u, and then bounded from 4 to 8. So I'll plug in the upper boundary. It's negative 2 over 8 minus negative 2 over 4. So that's negative 1/4 plus, we'll call that 2/4, which is 1/4. One thing I want to point out here is that I'm writing new boundaries because I put it in terms of u. Now notice that when I did my u substitution, I did not put it back in terms of x. I'm just leaving everything in terms of u. If you wanted, and it would be more work, you could put everything back in terms of x. So in other words, you can call this negative 2 over 4x squared plus 4, and then keep your x boundaries, which are from 0 to 1, and then proceed from there. And you would also end up with 1/4. But I think it's more work to do it that way, but it can be done. So you have to remember that if you have your boundaries in terms of u, then you leave your integral in terms of u. If you're going to keep your boundaries in terms of x, then you're going to have to go back and put your expression in terms of x.